Hi. Today we will talk about the Thevenin's theorem, which is very fundamental theorem which is used for solving certain problems in electrical engineering. Before we start considering the method or procedure of using the Thevenin's theorem for solving certain problems, I just advise all the viewers to just go through my first lecture or say earlier lecture which was on Kirchhoff's laws. That lecture has also been online since a few days, and so in that initial lecture I had explained what are Kirchhoff's laws, how they are implemented in the given circuit, and then how to distribute the currents using first law, how to write loop equations and all that. Why that knowledge is necessary? Because in the procedure of solving any such problem or electrical circuit, using Thevenin's theorem needs all these things to distribute the currents, to write loop equations and all such things. So it is advised that the viewers please see the earlier video on Kirchhoff's laws. Now see, in that video I had taken certain problem, and the problem statement was to find the current in this 8 ohm resistor. So it was the same circuit that was used: 20 volt battery, 8 volt battery, 4 volt battery, all these batteries in given type of connections or the polarities, and such resistors connected in certain combination. Okay, the benefit of taking the similar problem or same problem here is that once we arrive at the solution with Thevenin's theorem, we can easily cross check whether our answer is correct or not, because we earlier have found out the solution for this problem. So I have written here the problem statement. The problem statement is find the current in 8 ohm resistor using Thevenin's theorem, and this is the circuit. Okay, so problem statement is fixed now, to find current in this 8 ohm resistor. Now today I shall tell how to solve this particular problem and find this required current through this 8 ohm resistor using Thevenin's theorem in 5 simple steps. Okay, so those steps we have to always keep in mind so that we can solve any such type of problem. I had earlier told in the earlier lecture that the problem cannot be only like this, to find current in this 8 ohm resistor. The problem can be to find power in 8 ohm resistor. You know that again, that would be one more simple calculation which is added in the solution. So just if you find out the current in this 8 ohm resistor, then once current is known, then power, you know that it is I squared into R. Now see, the problem can be anything. I may ask you to find current in this 4 ohm resistor, or in this 4 ohm resistor, in this 2 ohm resistor, and so on. So problem can be anything. But since we want to repeat the same problem here so as to verify our answer later on, we just maintain the problem same. Only what we have changed in the problem statement, that now we solve it using Thevenin's theorem. So I will tell you the 5 simple steps to solve such a problem. Now step 1 in Thevenin's theorem is the resistor in which you want to find out the current should be denoted. In step 1, the resistance in which the current is to be calculated should be denoted by, or we can say that it is our load resistor. Okay, we say that it is our load resistor. Normally load resistor is shown as R and L suffix. Okay, so in our case this 8 ohm will be denoted henceforth as the load resistance RL, or load resistor RL. So first step. So step 1 says that you first remove the load resistance from your circuit. Step 1 says that you first remove the load resistor from your circuit. Now once I do that, then this will be the situation. I have to remove this, so just I show that it is not there here. Okay, and then I get such 2 open terminals, and I show this 8 ohm resistor somewhere here away from the circuit right now, because we have removed it. So this 8 ohm resistor now becomes our load resistor RL. Okay, and then whatever open terminals we get, we mark these open terminals by some names, or say by some letters, like say A and B. So that is just for our own convenience that we are doing this. You may say X, Y, M, N, or anything like that. So what is our first step? Our first step is that we have removed our load resistor from the circuit, and then we have marked the open terminals as A and B. Okay. Now see the fundamental idea of the Thevenin theorem, what Thevenin has suggested or what Thevenin has said about his theorem. Remember, Thevenin is the name of a person who has suggested this particular theorem. So again, as I always give stress that whenever you are concerned with the names of various persons, you write the spellings very neatly. So Thevenin, Thevenin. And as he has suggested this theorem, it will be Thevenin's theorem. Now remember some fundamental difference between this type of theorem and the normal or usual Kirchhoff's laws. In Kirchhoff's laws, once you write the equations, solve them, find various branch currents, at one and the same time, finally, you get currents in all the resistances. Whereas this theorem is a problem specific. For example, our problem is to find current in this 8 ohm resistor. So here this becomes problem specific, means this will give you answer only for this, that you will find the current in 8 ohm resistor finally. If your problem would have been find current in this 4 ohm resistor, what we would have done, this 8 ohm would have been at the same place. However, we would have removed 4 ohm and we would have marked the open terminals as A and B. So this is the main idea, that it is a problem specific type of the theorem. Now see, once we remove the theorem, see what basic idea Thevenin has suggested. Thevenin said, once you remove the load resistor, then suppose this particular box or space, okay, like this. So there is something in this particular box which I have marked with this red line, okay. So something is there. It may be a black box. We don't know. It has a combination of some voltage sources, some resistances like this. But finally, from out of the box, if you look, suppose from here, what you will find? You will find that some box is there. It contains some circuit. Circuit may have power sources like voltage, current sources. Circuit may have certain resistances connected in certain fashion. But from outside, we see only two open terminals, A and B. Thevenin said that this, whatever we get now, after removing the load resistance and after marking these two terminals, A and B, whatever we get, it is called as a two-port network. So A is called as a port, B is also called as a port. So from this side, if I look, then these are the two ports. And then there is some circuit in this red box, okay? So Thevenin said that when you come across such a two-port network, then suppose we connect a voltmeter like this across these two ports. Suppose I connect some voltmeter from outside, okay? A DC voltmeter. If we connect, then it will give some reading, or it may give some reading of voltage here. So what is that voltage? So from looking outside, what we get is some voltage between A and B. Definitely that is some voltage created by this circuit which is enclosed in the box. So finally, means his idea is, under this situation, points A and B will have some potential difference or some voltage created between A and B. Thevenin said that this is some open circuit voltage, and now normally it is denoted by VTH, okay? So VTH is nothing but Thevenin's voltage, but its meaning is that it is the voltage or potential difference which exists between point A and B due to the action of this entire circuit, okay? So that we call it now as Thevenin's voltage. So meaning is, again I repeat, the meaning is Thevenin's voltage VTH is nothing but some potential difference or some voltage which appears across open points A and B, or these two ports, okay? Now further Thevenin said that that is not the only thing which was there in this red box, but the red box also contains some resistances connected in certain fashion. So Thevenin said that if you look inside these two ports, suppose this is me and I am looking inside the circuit, whatever is there in box, what I will find? I will find that this entire network of the resistances will give one equivalent single value of resistance between these 2 points, some single resistance between these 2 points. We call this resistance as Thevenin's equivalent resistance, or say RTH. Remember this TH we call it for remembering Thevenin who has suggested this theorem. So what is RTH? RTH is some equivalent resistance of the entire passive network of the resistances which contains in the box. But remember, for determining this RTH, which is some equivalent single value given by the entire network in the box, while determining that value, remember, you have to assume that the power sources are not acting, they are not there. It is just a passive network. Now in that procedure, which we will learn in the earlier next steps, one of these steps next, we will find that if there are voltage sources, then they should be replaced by their internal resistances. Means what? If this 20 volt source has some 1 ohm resistor, what should I do? While determining the Thevenin's equivalent resistance, I should just represent that voltage source with its 1 ohm internal resistance. But if they have not specified any internal resistance of the voltage source, then no resistance means zero resistance, then you have to just short that branch. So voltage sources, ideal voltage sources will be shorted like this. For this also, this will be shorted like this if it does not have any internal resistance. Also for 4 volt, if it does not have any internal resistance, then you have to short it. So finally you will find that it becomes a passive network or inactive network just composed of the resistances. Okay, so basic idea for determining RTH is that you have to only consider what would be the final single value of equivalent resistance across these 2 points given by this entire network in the red box. Okay, so that is the idea, but we will go to that point later on at the appropriate step. So I again restore our circuit because we have to start right from first step onwards. So I will just write or replace my voltage sources. 20 volt was here, then this was the source which was 8 volt here, and here there was one source, this was 4 volt here. Okay, so I have just redrawn the circuit because we want to start from our initial point. So what is the idea given by Thevenin is that when you remove the load resistance, then you get 2 open ports like A and B. Then the entire circuit in the red box will give some open circuit voltage or potential difference between points A and B. I just remove the voltmeter now because that was I had shown just to explain the idea of open circuit voltage. So that single value of voltage across A and B, which is the VTH now, and that single value of the resistance, which is equivalent to the entire passive network inside the box, is now RTH. Once you are able to find out these 2 values, that means it is clear that whatever was the circuit or whatever is the circuit inside the red box can be replaced by the single voltage source VTH in series with the single resistance RTH. Means what I am going to do, the circuit will be like this. This red box, just I will show that red box. It was this our red box having that circuit. We were seeing only 2 terminals from outside, A and B, like this. And once we find VTH and RTH, what does it mean? It means that this entire thing in this box I can represent with one single equivalent voltage VTH. What was its meaning? Meaning that I had told you, this VTH value is nothing but the open circuit voltage across points A and B. And then in series with this, there will be one single resistance RTH. So the circuit finally becomes like this. Okay, like this. Okay, so the fundamental or the central idea of Thevenin's theorem is that you should treat this circuit or operate on this circuit in such a manner that you finally decide what is VTH, single value, and what is RTH. And once I do that, or we do that, we can replace this entire circuit in the box with the equivalent values. And once we do this, the next step is very simple. Whatever you had removed from points A and B, we had removed from points A and B, we reintroduce or reconnect in the circuit. So I just replace or reconnect or reintroduce my RL here. okay, because I had earlier removed it. I had removed it for only a purpose of deciding VTH and RTH. Once we decide those values, we will just put it at its own place. So this circuit becomes equivalent to this circuit. And now see, this is a simple series circuit where we can use Ohm's law for determining the current. Suppose the current taken by RL, load resistance, is some current I ampere. Okay, just use your Ohm's law and tell me what would be the answer for the current. Simple. What is the total voltage acting in the circuit? Is VTH. What is total resistance acting in the circuit? RTH in series with RL. So what would be the current value I? The current value I would be equal to VTH divided by RTH plus RL. So this is the simplest idea that Thevenin has suggested for finding out the current in the given load resistor. Okay, so simple central idea. Such a given circuit, we want to find out current in any given specific resistance. We remove the resistance, call it as a load resistance. Once we remove it, we get the two open terminals. Then across open terminals, we perform certain operations. You make use of certain laws or certain procedures so that we find the open circuit voltage across points A and B, which we represent as VTH, and we find the net or equivalent resistance of the entire circuit in this box as seen from these two ports. That single value is RTH. Once we do that, we put the circuit into this fashion. Now we get a simple circuit. We reintroduce the load resistance across points A and B after determination of VTH and RTH, and then it becomes a simple series circuit where we can make use of Ohm's law. And Ohm's law says that current in any such circuit will be the total voltage acting in the circuit divided by the total resistance across the source, voltage source. Total resistance is RTH plus RL and the total voltage acting is VTH. So I will be equal to VTH divided by RTH plus RL. So this is the answer because we have shown I as the current in your RL. Okay. So we have to solve this particular problem using certain steps. I have told you that we can do that in 5 very easy steps. But once we understand the steps involved, we will find that we can solve any such problem using the same 5 steps. Okay. So the first step was we have removed the load resistance of 8 ohm from the circuit. Okay, this was our RL. Okay, now we get such a circuit or network, 2-port network. I will just remove the box now. We don't want now the box in the circuit or around the circuit. That was just to explain the central idea of Thevenin's theorem. Okay. So this circuit remains after removing the load resistance. Okay. So just I make the circuit clear. Okay, point A, point B. So this will be the first step. Now as a second step, what should be done? In second step, you have to now assume that your given circuit is this, not this RL. Okay. Even we can just remove it from blackboard, so that it does not come into the main circuit at this stage. Okay. So now you have to assume that this is your given circuit. Next step, step 2 is distribute the currents in the circuit that we have so obtained after removing the load resistor. Distribute the various branch currents, then write different loop equations using Kirchhoff's law, and finally find the currents that we have distributed. For example, now I assume here that you have seen the earlier video of using the Kirchhoff's laws. So now as if we know the concepts, and from that point we will go on. Suppose I start distribution of current from this place. Suppose this is I1. Now see, whether at the beginning you will come to know how many current variables you have to use, whether 1 or 2 or 3. Generally, it can be decided by looking at the number of meshes. Mesh is a smallest loop. So you will find that this is a smallest loop and this is a second smallest loop. Whereas now this will not be any loop because these terminals are open. So you find that there are two smallest loops. So the current variables will be 2. So I start like this. Suppose I start the current distribution from this point. Okay, I1. Then it will reach here. Here there are two paths, in this 4 ohm and in this 4 ohm. Suppose some current, we assume that this is I2 coming down. So what will be current in this 4 ohm resistor? It will be I1 minus I2. Okay. Now see, this I1 minus I2 will reach up to this point. Okay. It will reach up to this point. Now can the current go ahead? No, because it is an open circuit. So no current will flow through this particular branch. That means the entire I1 minus I2, from this point it will come down. So that I mention here as I1 minus I2. Okay, coming down. Now this current will reach here. Again there is no bifurcation from this point because ahead there is no closed circuit. It is just open terminal. So all that I1 minus I2 will come through this branch like this. Okay. So it will be like this. Now this I1 minus I2 comes over here. This I2 comes over here. They will add, and what will be the current going next? Will be current I1. And now you will find that you had started from this point and you are returning with the same amount of current. Our current distribution is proper. So what is the second step? Second step will be to distribute the current using Kirchhoff's first law or current law. Okay. Now here there is no end of the second step. Further we have to do something more in this step. Once we distribute the currents, our next thing is to identify the loops. Okay. Now we have two variables, I1 and I2. That we have to find out. So we will need two equations. Now how many loops are available? This is one loop available. This is the second loop available. And this is the third loop available. You cannot take this full loop because this is open circuit here. So for our own convenience, we will take these small meshes like this. Okay. I call this small mesh as 1 or loop as 1 and this one as 2. So my loop 1 will be from this point here, then down, then left, and then again to the original point. And my second loop will be from this point up to here, then down, back here, and again to the original point. Okay. I need only 2. So I have just mentioned 1 and 2. Okay. Now our job is to write the loop equations. So for loop 1, just we write the equation using Kirchhoff's second law. Suppose for loop 1, we start from this point. This to this, we are traveling clockwise. Our current is also in the same direction. So it will be, the voltage drop will be minus 2 I1. So while we reach to this point, the voltage drop will be minus 2 times I1. So minus 2 I1. Okay, now we reach to this point. Now this to this. Again, we are traveling clockwise, means downwards in this branch. Our current I2 is also downwards. So it will be again a voltage drop. So minus 4 times I2 will be the next term here. So minus 4 times I2. Now we have reached here. This to this point, no resistance, no components or no voltage source. That means no question of any voltage drop or rise. And this point to this point. Again, as I have told you earlier, you are jumping from negative plate to positive plate while traveling. Okay. So it will be a voltage rise. So voltage rise will be by 20 volt. So plus 20 volts. And now you have reached to the original point from where you had started. We have considered all voltage rises, voltage drops in the given loop. And that means this sum total must be equal to 0. Okay. So now just make it a simpler one. If we divide by minus 2, it will be I1. So I can write that is I1 plus 2I2 equal to 10. Okay. This I call as equation 1. Because 20 I take to other side, it becomes minus 20, and when we divide all the terms by minus 2, it will become 10 to right hand side. And now for loop 2. Again we have selected already the loop 2. We have to just write the equation for that. Suppose we start from this point and we traverse the loop 2 in this particular manner. Now this to this, 4 times I1 minus I2, plus or minus means drop or rise. See, you are traveling clockwise. This current I1 minus I2 is also in your same direction. So minus 4 times I1 minus I2. So minus 4 times I1 minus I2. Okay, now you have reached here. Now our traverse is like this. Okay, so when we are coming down, see, our travel is clockwise, that means we are coming down. The current I1 minus I2 is also coming down. So again it will be a voltage drop. So minus 2 times I1 minus I2. Now next, we have reached up to this point. Now this to this, no resistance, but there is a battery. Now see, when we are traveling this to this, we are jumping from, we are first reaching plus plate, positive plate, and then we are reaching negative plate. Means we are jumping from positive to negative. So voltage will drop. So this I have to write as minus 8. So minus 8. Now we have reached up to this point. And now last travel from this point to the original point from where we had started. Now see, we are traveling from down to top because we are traveling clockwise, but your current I2 is downwards, means it is opposite. We are traveling from down to top and the current is from top to down, top to bottom. So this current is opposite. Now it will be a voltage rise. So voltage rise will be 4 times I2, but we have to take it as plus 1. So plus 4 times I2. And now we have reached to the same original point from where we had started. This all must be equal to 0. Again, next step, that make it simpler. Okay. So I1 terms, minus 4I1 minus 2I1 will be minus 6I1. So minus 6I1. Now I2 terms, plus 4I2 plus 2I2 is 6I2. 6I2 plus 4I2 is 10I2. So plus 10I2. Remember here, as I had already told, even in the lecture of the Kirchhoff's law, that while distributing the currents or while writing the loop equations, somewhere at any place, if we go wrong, by even making mistake in writing the positive or negative signs, the entire problem will be wrong. Okay, so very carefully we have to write these equations and solve them. Okay, so we again check minus 4I1 minus 2I1. These are the only I1 terms. So minus 6I1. For I2 terms, plus 4I2 and here plus 2I2. 4 plus 2, 6, and this is 4I2, so 10I2. And this 8, we can take it to, that is the only constant, we can take it to other side, so this will be equal to 8. Further, we can make it somewhat shorter by dividing by 2. So minus 3I1 plus 5I2 equal to 4. Okay, so we cannot further simplify it, so we let it be like this, and we call this as now equation 2. Okay, we call this as equation 2. So we have two variables. We have written equations for two selected loops, and now our next job is just to solve this equation 1 and equation 2 and then find the values of I1 and I2. So that will make the end of the step 2. So here again we revise. What was our step 1? Our step 1 was the resistor in which we have to calculate current is removed from the circuit and we denote it by load resistance RL. And in second step, whatever circuit we have got, by removing the RL, we consider that circuit, distribute the currents in various branches, then select some typical loops, okay, whatever we want as per the number of current variables, then write the loop equations like this, and finally solve the equations and finally find the values of current variables. So the solution of these two equations, equation 1 and equation 2, will make end of our second step. Unless we do that, we should not proceed to the step 3, because step 3 will require these values of these current variables. Okay. So if we solve those two equations, equation 1 and equation 2, you will find, because we will not waste the time in the explanation of the particular theorem, Thevenin's theorem. So directly I will tell you what would be the solution. We will get I1 as 42 by 11 ampere. A plus value we are getting with the given current distribution, and I2 value we will get as 34 by 11 ampere. Okay. So if you solve these two equations, you will find that you get these values. We are getting plus values here. Let the values be plus or minus. We are not bothered of that at this particular stage, because we know that what is the significance of plus or minus signs. If we get some answer as minus, that means that finally in the final current distribution, the current must be in the opposite direction. Okay. So we are not bothered at this stage in the solution of Thevenin's theorem at this stage. Okay. So we have reached to the end of the step 2. Remember now. Okay. And now here onwards, we have to move to step 3. See, now that is the most important step in this particular theorem. Okay. And also very interesting. Okay. I just scratch it here now and write the step 3 as to find VTH. So what is our step 3? Our step 3 is to find the value of VTH. And as I have earlier told you, VTH is nothing but the open circuit voltage that will appear across points A and B in the circuit. Now how to calculate this VTH? For that one simple thing. We assume here that some imaginary voltage source is connected between points A and B. So I will just show it like this. Okay. So what is our assumption here? That some imaginary voltage source is acting across points A and B. Okay. That means we close for the time being, momentarily, these points A and B with a DC battery. Now there are two options. Somebody may show battery like this, positive terminal upwards, negative downwards, means positive to A, negative to B. It is your choice how to show it. You may show a reverse way, that the positive terminal connected to B and negative to A. Also, see, that is immaterial at this particular stage. So you assume any orientation of the battery, but you should say that there is some voltage source acting, and which is imaginary source acting between points A and B. Okay. Now once we do that, what should be done next? Next thing is that you select, after connecting VTH like this, you select any loop, any closed loop or any closed path which will contain VTH. Let us find out how many loops we get. Okay. We want any one, but let us see how many loops we get which will contain VTH. For example, I will take this entire full loop. See, VTH is covered. So this is one. Or I may cover from this point, this particular loop. Still it is covering this particular VTH. Or I may take this small loop. It is also covering the VTH. So I can get 3 such loops where VTH will be contained in the loop. Okay. But we want only one. So let us select this particular loop here. Okay. The small loop, local loop here. Okay. We select it. Because if we select bigger one, unnecessarily these additional terms will also be there and the equation may be very long equation. So we just select this particular small loop. See, now our loop is like this. Okay. Now it is containing VTH. Let us start from this point and write the loop equation. So the step 3 says that, in which we are finding out the value of VTH. The step 3 says that we have to consider some imaginary voltage source, DC source, acting between points A and B, and the polarities we can assume like anything, this polarity or opposite polarity. And then we have to select one loop which will contain the given voltage source. Let us see now what happens. We write the loop equation for that. So for this loop, we will write the loop equation. Suppose we start from here. Now see, our travel is clockwise, as shown by this yellow arrow. Our travel is clockwise. Is there any current which is flowing in this 4 ohm? See, we have not to distribute currents now. With the previous current distribution and answers, we are moving ahead. So when I start from here, I know that in the previous current distribution, there was no current in this 4 ohm branch. So no current, so no question of any voltage drop or voltage rise. Okay, so we reach up to point A. Now from point A to B, we come across a voltage source. Okay, but see, we are jumping from positive to negative. So this we will write as minus VTH. Okay, as per our same previous laws. Okay, so from A to B it will be minus VTH. Now we have reached up to point B. Now B to this point. So this to this travel. Again there is no resistance, nothing, but there is a voltage source. Here we are jumping from negative to positive, so voltage will rise. So what we should write? Plus 4. So here I will write plus 4. And now we have reached to this point to this point, original point from where we started. See, we are moving upwards, but the current is I1 minus I2 is moving down in this branch. So it will be a voltage rise. So plus 2 times I1 minus I2. So plus 2 times I1 minus I2. And now we have reached to our original point, and this will be equal to 0. So this now we will simplify for finding out value of VTH. Hence I can write that VTH must be equal to what? I take VTH to one of the sides. So 4 plus 2 times I1 minus I2. Now here we substitute the values. So equal to 4 plus 2 times I1, the value I1 and I2 values we have already calculated in step 2. That you have to introduce. Introduce those values or put those values with whatever signs you have got, plus or minus. Don't change those signs. That is very important. So I1 we have got as plus 42 by 11. I2 we had got as plus 34 by 11. Okay. So both values we had got plus. So we have written plus values, and this is a subtraction, so subtraction sign. So this will give us 4 plus 2 times in bracket 42 by 11 minus 34 by 11 gives you 8 by 11. So it becomes 4 plus 16 by 11, and finally this will be equal to 60 by 11. So 60 by 11 is the answer for our VTH. As this is a voltage, you write the unit as volt. Okay. So this is the answer for our VTH. So very simple thing. So what we have done in step 3? In step 3, we have assumed an imaginary or fictitious voltage source across those open ports A and B. In any direction we can assume it. And then we have selected one such loop which contains the VTH. Here we had selected this small loop or small mesh. And then we have written the equation for that loop. And finally we have solved the equation to find value of VTH. In this, we needed the values of current variables. That was the reason why step 2 is there. So step 2 gives us this particular current variable values, and those are now useful to us in step 3. So step 3 finally should give you the value of Thevenin's voltage or open circuit voltage. So it is 60 by 11 volt. Now see, it may be a question that suppose I would have chosen any other loops. So I will just write in the corner so that we should not forget it. So VTH we have got it as 60 by 11 volt. And now just we will see what happens if suppose anybody else selects any different loop, but still whether we can get the same value of VTH. For example, if we select this particular loop, this one, okay? Let us see what equation we can write. Now see, our travel is clockwise like this. Current is also in our direction, so minus 4 times I1 minus I2. Then next we have reached here. Again ahead, no current in this 4 ohm, so no question of voltage rise or drop. Then here down it will be minus VTH. So we have reached here. This to this point plus 4. Then next from this point to here. Now see, this battery is opposite. We are jumping from positive to negative. So voltage drop by 8. So minus 8. Now we have reached up to this point, and this to this. See, we are traveling from bottom to top, whereas current I2 is top to bottom. So it will be a voltage rise again, 4 plus 4 I2. So plus 4 I2. So this all must be equal to 0. Let us just solve it. Okay. So minus 4 I1 plus 4 I2 minus VTH plus 4 Plus 4 and minus 8 will be, say, minus 4 plus 4I2. This all must be equal to 0. So minus 4I1. Then plus 4I2 and plus 4I2 plus 8I2. And we take VTH to other side. VTH and this 4 will mention here, minus 4. And we take this VTH to other side. Okay. Now let us introduce the values again. Minus 4 times. What was our I1? Our I1 was 42 by 11. Plus 8 I2. What was our value for I2? 34 by 11. Minus 4. So at this step, we have put the values of I1 and I2 as we have got earlier. So these values, let us further simplify it. This wall will be equal to, this will be minus 168 by 11. Then this will be plus 272 by 11. Then minus 4 must be equal to VTH. And then that means VTH must be equal to, just the simple calculation of these fractions and all that. This will be how much? This addition of these two terms will be so it will be 104. So this will be plus because 272 is big. So 104 by 11 minus 4. Just further it will be like this, 104 minus 44. Again you will find that this gives you 60 by 11 volt. So just match with our previous answer. This we had obtained with some different loop. So any loop you take, you will find that your answer must be same. Now the same thing you can do it. Suppose even if you take this bigger loop, right from this to this end, and if you write the loop equation, put values of I1 and I1, you will find that still you will get the same answer. Okay, so step 3 we are using for finding out the value of VTH. And now we move to the step 4. We move to step 4. Step 4 is to find RTH. Okay, so that equivalent resistance of the entire network across open points A and B. Okay, that will be our step 4. Now what is to be done in step 4? In step 4 now we don't want anything from all this data, any current distribution, nothing. What we want for step 4 or for finding out RTH, we just want the value of equivalent resistance as seen from these two terminals, and that value will be just the single value of equivalent resistance. So we need a passive circuit, as I have told earlier in the beginning. So we are in need of the passive circuit. So that passive circuit I will just represent here. Okay. So the circuit that we will consider for finding out RTH will be just this one. Okay. So this circuit will be a circuit that we have got earlier in first step when we removed the load resistance. Okay. Point A and B. Now where these voltage sources have gone? It was a voltage source with 20 volt connected here. It was a voltage source 8 volt at this place. It was a 4 volt source at this place. But why we have not shown them in our this resistance at our 4th step? I have told you that we are bothered or concerned only with the passive network which does not contain any power sources, neither voltage sources nor current sources. But there are certain rules when we want to eliminate or when we don't consider them in the circuit. As I have told you that if it is mentioned in the problem that these voltage sources have some internal resistances, then we have not to just short these points like this. suppose I had told you earlier that this, if suppose this 20 volt source has 1 ohm resistor, then you should not write the circuit like this, else you should have shown that 1 ohm here. Also, same case, if they had mentioned some resistance for this voltage source or some this voltage source, internal resistance, then you should have shown at the appropriate places. However, we are assuming in this problem that the sources are ideal because they have not mentioned any internal resistance in the problem. What was our problem? Find the current in 8 ohm resistor using Thevenin's theorem. Here they have not mentioned what are the internal resistances of these voltage sources. So no internal resistances, so zero resistance means it is a short circuit. Also remember at this stage that in some problems, means it is not that there will be always the voltage sources or batteries, these voltage batteries like this. There can be current sources also involved. Maybe there is a combination that there is one voltage source, at some other place some other current source. Remember, if these voltage sources are ideal, means if they don't have any internal resistance, and if it is a voltage source, then you have to short it like this. But if it is a current source, you have to open it like this. Okay, open. For example, if there would have been a current source here at this place, for example like this, some current source, but they have not mentioned some ampere value, and if they have not mentioned that, they have not mentioned any internal resistance for this. Now, as we have closed or shorted the voltage source, for current source we have to open circuit it. So simple rule, for voltage source it will be short circuited, for current source it will be open circuited. Means in that circuit this source will be open circuited, means it would have been this thing, this situation. So voltage source is shorted and current source is open. But since our original circuit has only these 3 voltage sources and also internal resistances are not specified, then all our 3 voltage sources will be short circuited. So our circuit finally becomes passive circuit like this. Okay. So only these 5 resistances, I will just write the values: 2 ohm, 4 ohm, again 4 ohm here, then 4 ohm, 2 ohm, that's all. Okay. So to find RTH, which is the final the unique equivalent value of the internal resistance of this entire circuit, or equivalent resistance of this entire circuit as seen from terminals A and B, for that calculation you have to consider only a passive circuit replacing the voltage or current sources as per the rules as I have just told you. So this is the circuit. So our next job is to just solve this circuit and to find out single equivalent value of resistance across these 2 points A and B. Okay. So that job you have to perform now. Now see, you will find 2 ohm and 4 ohm. They are in parallel. This is one branch, this is another branch. So across these 2 nodes, this is one branch of 2 ohm and this is one branch of 4 ohm. So 4 and 2 are parallel. What is the parallel combination? R1, R2. If R1, R2 are in parallel, what will be the net resistance of parallel combination? It will be R1, R2 divided by R1 plus R2. So 4 2s are 6 divided by 4 2s are 8 divided by 4 plus 2 is 6. So for these two, what will be the net resistance or parallel combination? Final answer 8 by 6. 8 by 6 is 4 by 3. That means my circuit is now reduced like this. Instead of 4 and instead of both of them, I will write here what value? 4 by 3 ohm. Okay. Now the circuit is reduced like this. Further we have to simplify it or reduce it. Now see, this 4 ohm is in series with this 4 by 3. When they are in series, we have to add them. So 4 plus 4 by 3 is 16 by 3. So instead of these two, I will show only one and with value 16 by 3. So your next circuit will be this one. 16 by 3 ohm. Further we have to simplify. Now 16 by 3 in parallel with 2. So again, as they are in parallel, R1, R2 divided by R1 plus R2. Just here I will make simple calculations or rough calculations. So R1, R2 is 16 by 3 into 2 divided by addition 16 by 3 plus 2. So this will give you 32 by 3 and this will give you 22 by 3. So finally it will be 32 by 22, or if we further simplify, it will be 16 by 11. So finally these two will give you 16 by 11. Okay, so instead of these two, I will just show one as 16 by 11 ohm. And finally, one more simple calculation, that these two are in series. So 16 by 11 plus 4 will be giving you 16 by 11 plus 4 will be giving you 60 by 11 ohm. Okay, so finally I can write this circuit as like this. Our point A was here, our point B was here, and just one final value of resistance that we got as 60 by 11 ohm, and this is nothing but our RTH. So third value that we needed, I will write it here. We are compiling the answers in each step. So here RTH I will write as 60 by 11 ohm. Now maybe these two values you are getting same is just a coincidence. Okay, it is not every time like that. Okay, so these values we have got in our all these first 4 steps, and finally you can represent your entire given circuit with this very simple circuit. We know that our simple circuit finally must be in the form like this. Okay. Okay, we must have our circuit finally in this form, where this must be VTH, this must be RTH, and this must be our RL. Okay, so this circuit now we will draw for our given circuit. A battery source VTH, but this value we have calculated as 60 by 11 volt. So I will write here 60 by 11 volt. Then a series resistance RTH. But this value we have calculated, it is 60 by 11 ohm. And across these 2 points A and B, it is our load resistance, which is already mentioned in the problem, that is our 8 ohm. So 8 ohm here. Okay, Thevenin said that you can convert any such circuit in this particular form finally. Okay. And now the solution is very simple. What was our problem? Our problem is find the current in 8 ohm resistor. So this is the final circuit that we are getting. This is our 8 ohm resistance or load resistance. I assume that this current is some current I. Okay. And what is the answer for I now? The answer will be like this. I must be equal to, see what is total voltage? 60 by 11. So I must be equal to VTH divided by RTH plus RL. We just substitute the values. VTH was 60 by 11. RTH was 60 by 11 ohm, and plus RL was 8 ohm. Sorry. Here we may not write the units. Okay. So this is it. And if we calculate this particular thing, that will be the final answer for the problem. So let us just calculate that. 60 by 11 divided by all that. So here we make a rough calculation. So I must be equal to 60 by 11. In denominator what we will get? 148 by 11. So finally it is 60 by 148. If we divide further by 4, numerator will be 15, denominator will be 37. Okay. So this is the final answer. Okay. So this is the final answer for the given problem. Okay, so this is in short the procedure of solving any such problem with the help of Thevenin's theorem in 5 simple steps. Remember, what can be the problem given like this: any type of circuit, any voltage or current, any power sources, voltage sources or current sources, any combination of the given resistances, any values for the sources and resistances. The procedure remains same for solving with Thevenin's theorem. So any such problem can be solved in such 5 simple steps. Okay, that is the central idea of Thevenin's theorem. I once again say that this theorem is a problem specific. That means our problem was to find out current in this 8 ohm resistor connected here. So the problem was oriented around these two terminals. Okay, for VTH, RTH and all that. The problem can be different, that somebody may ask you in the same circuit to find some current in any of the other resistors, but then those terminals will be open terminals there and the problem will be oriented across those 2 points, open points A and B. Okay, so this is a problem specific or resistance or say component specific type of theorem. Okay, but a lots of practice will be needed for making mastery on the application or the use of the Thevenin's theorem. I take a very simple problem for another illustration of or for the use of these 5 steps of Thevenin's theorem. So we take a simple problem here. I just take one voltage source here, say, or a circuit like this. Okay. And maybe the values would be like this: 8 volt here, 4 volt here, and these resistances of 2 ohm here, 2 ohm, 2 ohm, and say 4 ohm here. And suppose I mention a problem, find current in 4 ohm resistor. Okay, obviously using the Thevenin's theorem. Okay, so let us implement the steps. What was our first step? Our first step was to identify the load resistance and remove it from the circuit. What is the load resistance? Because we want to find out current in 4 ohm resistor, so that becomes our RL or load resistor. So our first step will be like this. We will write here in some corner that load resistance is equal to 4 ohm. Okay. Once we mention that that is a load resistor, then what is our next step? To remove it from the circuit. Okay. So I just remove it from the circuit. So finally I will get this particular situation. Okay. So now these two terminals become open after I remove the load resistance. So I will just mark A and B. So first step is over, that we have removed the load resistance, written its value in some corner, and this is our circuit. Next is what? Second step, to distribute the currents in various loops, those are available. Write loop equations and find out the values of various current variables. You will find that if you try to say distribute the currents, you will find that you get just one single loop like this. Because see, this branch is open now. Otherwise in the given circuit, you had this loop as first, this as second, and the entire one as third. But now the removal of load resistance has made it just a single loop. So I want just one single current variable. I just assume that this is current variable I. See, it will come here. No question of flowing any current in this branch because that is open now. So same current I will move ahead. Then same current will come down here I. Same current in this resistor I. Again there is no question of any current flowing here. So same current I here. And see, finally you come to the original point. So this is the simplest current distribution for such type of circuit, because there is only one loop that is there now after the removal of load resistance. And what is the another thing remaining in step 2? That after current distribution you have to write the loop equations. How many loops we are getting? The clear observation of this particular diagram will tell us that we get only one single loop, and it is just this loop because now this is open. So this is the loop, one single loop that we are getting. We assume that we are traveling clockwise. Just let us write the loop equation. So our second step will be, loop equation will be just we start from this point. Now see, our travel is clockwise. Current is also in our direction, so minus 2I. Then we come up to this point. We have not to go like this. We have to move ahead. Now this is a battery. We are reaching to positive first and then jumping to negative, so minus 8. Then we reach here. Here to here, it will be minus 2I again. Then from this point to this point, minus 2I, because see, all these currents are in our same direction of travel. Okay. Then we have not to go here. So this to this, again minus 2I. And then one more thing remaining from this to starting point. So now you are jumping from negative to positive terminal of the battery. So it will be plus 4. So plus 4 equal to 0. So just to simplify it further, minus 2I, minus 2I, minus 2I and minus 2I. So minus 8I. And the constants are minus 8 and plus 4. So minus 4. This all must be equal to 0. This will give you minus 8I equal to 4. And this will give you I is equal to minus 4 by 8. That is minus 1/2 ampere. Okay. Now here we have got minus answer. Let it be minus. We have not to change anything, any signs anywhere in this procedure. So second step we have implemented. Now see step 3. What is the step 3? In step 3 we have to find out the value of VTH. Okay, to find VTH. So step 3 will be to find VTH. Now for this, what should we do? To find VTH, we have to assume an imaginary or fictitious voltage source across those open two terminals. I will just scratch now this arrow because we don't need it now. Okay. So in our step 3, we have to consider some imaginary or fictitious voltage source connected across points A and B. I will just show the source. Okay. Now maybe I show it like this, or maybe I will be showing in opposite manner. Again, forget, you can show it like anything. Okay. Positive to A or positive to B in any fashion. But here I will write that this is our VTH. Now once we imagine a voltage source across the two open points, then what is our next procedure in step 3? That consider any loop that will contain VTH. So suppose, let us look at the figure. I can consider this particular loop, it will contain VTH. Or I can consider this second one, it will contain VTH. But how many loops we have to consider? Only one, any one. So either you consider this one, left side loop, or you consider this right side loop. Any loop you consider, it must give you the same answer for VTH. Suppose we consider this left loop. And then write the loop equation. Again we start from this point, minus 2I. Then next. Now this is your loop, remember, because you have shown the voltage source across A and B. Okay. Now you reach to this point. Now you are moving opposite, means positive to negative, you will be jumping. So it will be minus VTH. Next, you have reached to this point. Now you have to go left. Again minus 2I. And from this point to the starting point, plus 4. So plus 4. This all must be equal to 0. Let us see what result it gives us. This gives VTH equal to minus 2 and minus 2, minus 4I plus 4. Okay. Now here you get the value of VTH, but this is unknown, but you have already calculated the value of I. Value of I was coming in earlier step as minus 1/2. So I will just put the value minus 4 in bracket minus half plus 4. So this will give you 2 plus 4. That means it is 6 volt. Our next step is to find RTH. So that will be step 4. So to find RTH. Now for that what we should do? We should take the passive circuit and we should replace the voltage or current sources appropriately with the rules. Okay. So what circuit we will get? See now this, they have further not mentioned whether the batteries have any internal resistances. So they are ideal batteries. So these 4 volt and 8 volt batteries will be just short circuited, and all the resistances will be kept as they are. So your circuit for this calculation will be this one. This battery short circuited, these points A and B open, and to right hand side this battery will be short circuited, this 2 ohm and also this 2 ohm. Okay, so 2 ohm and 2 ohm. So this will be just the circuit. And now see, it is very simple here to find out the net equivalent resistance across points A and B. These 2 and 2 will be a 4 ohm resistor, and also these 2 and 2 in series 4 ohm resistor. So your next step will be, instead of these two resistances, I will show just one single branch of 4 ohm. And for this 2 and 2 in series, I will show the sum 2 and 2 4. So the circuit will be reduced to this. Okay, and now further, these 4 and these 4 ohm, they are parallel across points A and B. So 4 parallel to 4 will make the value half. So finally your circuit will be reduced to just one single resistor across points A and B, and this value will be 2 ohm. And that is what we want. See, at this stage this 2 ohm will be called as the Thevenin's resistance RTH. So third conclusion, RTH I write here as 2 ohm. And now last step, to calculate the current. So our given circuit will be resulting finally into this VTH value we have got 6 volt, this RTH value we have got as 2 ohm, and our load resistance as defined in the problem was 4 ohm. Okay, so this is the circuit. And so finally the current flowing in given load resistance, if I show it with I, so simply using Ohm's law, what will be I? I will be VTH divided by RTH plus RL. So I will be, here I write, I will be equal to 6 divided by 2 plus 4. Okay, so 6 by 6 is 1 ampere. So this will be the answer. I thank you, all of you, for attending this second lecture on Thevenin's theorem. Thank you so much.